Sounds good.
So we're looking at chemistry, chapter 19, solutions and solubility. We'll start at the beginning, page 1 of 6.
Okay.
Section 1, the basics.
Mm-hmm.
What is a solution? It says here, it's a homogeneous mixture.
Right.
But the key here, what makes it special, it's got to be uniformly distributed.
Mm-hmm.
So it's not just, stuff mixed together.
Right.
It's evenly spread out.
Exactly. And section 1.1 on page 1 gives us some good examples of solutions to illustrate this point.
Examples of solutions, yeah.
The classic one, of course, salt dissolving in water. Like, you don't see the salt crystals anymore.
Right.
They break down into these tiny ions, and they're just completely dispersed throughout the water.
Okay, so like sand in water wouldn't be a solution.
No. Good point.
Because the sand would just settle?
Exactly. That would be what we call a heterogeneous mixture, not a solution.
Okay, heterogeneous.
But yeah, let's stick with solutions for now. So example 1.1 on page 1, salt in water, dives a little deeper. So salt, which is sodium chloride, NaCl, it breaks down into sodium ions and chloride ions, right? And then these ions, they get surrounded by water molecules. It's like they get pulled apart and spread out evenly by the water.
So it's not just like the salt disappears. It's like integrated into the water on like a molecular level.
Exactly. Yeah, exactly. And you see this uniform distribution in other examples too in section 1.1. They mentioned sugar dissolving in water or alcohol in water. Yeah. Even things like the carbon dioxide in soda, that's a solution.
Oh, wow.
It's a gas.
I never thought of it that way.
Dissolved in the liquid, and it looks the same all the way through.
Yeah, you don't see like bubbles in one spot. It's all just mixed.
Now, moving on to section 2 on page 1, this is where they introduce the terms solute and solvent. Crucial for understanding solutions. So solute is what gets dissolved.
Okay.
And the solvent is the substance that does the dissolving.
So in the salt water, the salt is the solute, the water is the solvent.
Exactly.
Okay.
And example 2.1, aqueous solution, shows how we represent the solvent in like chemical formulas, right?
Okay.
So they have nano3, AQ. That little AQ stands for aqueous, which means the solvent is water.
Oh, okay. Good.
So you immediately know that sodium nitrate, NaNO3, is dissolved in water.
Makes it easy.
Exactly. Yeah. Okay. Let's turn to page 2.
Page 2.
Section 3, dissolves. This is a key concept.
It dissolves
in insolubility.
So is this saying that certain substances are just meant to be together?
Kinda, yeah. It's all about the polarity of the molecules. Polar molecules have a slightly positive end and a slightly negative end, kind of like a tiny magnet.
Okay.
Water is a great example of a polar molecule.
Yeah, I vaguely remember that oxygen hogs the electrons or something.
You got it. So polar molecules tend to dissolve well in other polar molecules. They're attracted to each other because those opposite charges kind of line up. Non-polar molecules, on the other hand, they don't have these distinct positive and negative ends.
So it's like birds of a feather flock together, but for molecules.
Exactly. And they give a good example in section 3, fats dissolving in oil.
Okay.
Fats and oils are nonpolar, so they mix well. But oil and water, they don't mix because water is polar, oil is nonpolar.
That's why my salad dressing always separates.
Exactly. So this dissolves, is fundamental to understanding solutions. Now, on the same page, section 4, they go into properties of solutions. Specifically, 4.1, characteristics of liquid solutions.
Characteristics.
They list a few key features. First, they're homogeneous, meaning they have a uniform composition throughout. They're also clear, you can see through them.
Right.
And unlike our sand and water example, they don't scatter light because the particles are dissolved at a molecular level, right?
So they're perfectly blended smoothies, everything's evenly distributed.
Yeah, that's a good analogy. Another important point in section 4.1, solutions don't settle upon standing.
Okay.
So unlike suspensions where those particles eventually settle at the bottom, a true solution, it stays stable over time.
Like salt water, the salt won't just reappear at the bottom.
Exactly. Okay, moving on to section 5 on page 2, factors affecting solubility. This is something I've always been curious about. What makes a substance dissolve more or less easily?
What to fix it, yeah.
Temperature is a big one. Section 5.1 focuses on how temperature affects the solubility of solids in liquids. Generally, solubility increases with temperature.
Okay.
So think about dissolving sugar in your tea. You can dissolve way more sugar in hot tea than in iced tea. That's because the heat energy helps break down those sugar crystals and disperse them faster.
That's why my iced coffee never seems sweet enough.
Exactly. But gases, they behave a bit differently. Section 5.1 points out they become less soluble as the temperature rises.
Oh, interesting.
And they use carbonated beverages as an example.
Oh, like soda going flat faster when it's warm.
Exactly. Example 5.1 on page 2, carbonated beverages explains this. So the high pressure in a sealed bottle, it forces the carbon dioxide gas to dissolve in the liquid.
Okay.
But as the temperature rises, those gas molecules, they gain energy and they can escape from the solution more easily.
So that's why warm soda loses its fizz.
Exactly. Now, what about pressure?
Pressure. Yeah, section 5.2 mentions that.
Right, pressure mainly affects the solubility of gases and liquids.
Okay.
And there's a law that describes this relationship, Henry's law. It states that the solubility of a gas in a liquid is directly proportional to the partial pressure of that gas above the liquid.
So higher pressure, more gas you can cram in the liquid.
Exactly. Think back to the soda example. All that fizz is due to pressurized carbon dioxide. They use a lot of pressure to dissolve a large amount of CO2 in the soda, gives it that characteristic fizziness.
Wow, it's all science. Okay, let's turn to page 3. What else we got here?
All right, let's see.
Section 6, changes in freezing and boiling points. Oh, I remember vaguely learning about this, but I could use a refresher.
Yeah, me too. So section 6.1 starts with freezing point depression. Adding solutes to a liquid actually lowers its freezing point.
Wait, so you're saying if I dissolve something in water, it'll freeze at a lower temperature?
Exactly.
How does that work?
So those dissolved solute particles, they interfere with the water molecule's ability to form that, neat and organized solid structure, which is what happens when water freezes. So you need a lower temperature to get those water molecules to settle down and form ice.
Okay. But how does that, play out in real life?
Think about wintertime. They spread salt on icy roads.
Yeah, to melt the ice.
Right. That's because of freezing point depression. The salt dissolves in that thin layer of water on the ice's surface and lowers its freezing point. So instead of freezing solid at 0 degrees Celsius, the salty water stays liquid even at temperatures below freezing, helps to clear those icy roads.
Wow, that's a really practical application.
Right. It's everywhere. But we're not done with freezing and boiling points yet. Section 6.2 on page 3, boiling point elevation, kind of the opposite of freezing point depression.
Okay.
Adding solutes to a liquid, it actually raises its boiling point.
Really? So if I dissolve salt in water, it'll take longer to boil?
Yes, because those dissolved solute particles make it harder for the water molecules to escape from the liquid and enter the gas phase, which is what happens when water boils. So you need more heat energy to get those water molecules to break free and boil off.
Okay, so those little solute particles are really shaking things up.
Yeah, they add some complexity. Now, on the same page, Section 7 introduces another crucial concept, concentration of solutions.
Okay, so is this about how much solute is actually dissolved in a given amount of solvent?
You got it. It describes the strength of a solution, and there are several ways to express concentration, each with its own formula and applications. Section 7.1, page 3, kicks off with molarity or molar concentration.
Okay, I vaguely remember molarity, something about moles.
You're on the right track. Molarity is defined as the number of moles of solute per liter of solution. It's a very common way to express concentration in chemistry, especially when we're dealing with chemical reactions.
So if I'm making coffee, is that measuring the coffee grounds per cup of water?
That's a great analogy. It's about quantifying the strength of the solution. And just like you can have a weak or strong cup of coffee, you can have a dilute solution with low molarity or a concentrated solution with high molarity.
Okay, that makes sense.
So how do we actually calculate molarity? The document gives a clear example. Example 7.1 on page 3 shows how to calculate the molarity of a solution containing 4.0 moles of NOH, that's sodium hydroxide,
Okay.
dissolved in 0.5 liters of solution. They plug those values into the formula and they get a molarity of 8.0 M. M stands for molar.
So that's pretty concentrated then.
Exactly. It indicates a high concentration of NaOH in that solution. Now, before we jump into the other ways to express concentration, any questions on molarity?
I think I'm good for now. But what are those other ways to measure concentration?
Well, like I said, there's several other ways, each with its own formula and use. Want to explore those now or move on to the next page?
Let's hear them. I'm curious about these other concentration calculations. What's percent by mass, section 7.2?
Okay, percent by mass, pretty straightforward concept. Page 3, section 7.2, defines it as the mass of the solute divided by the total mass of the solution, and then you multiply that by 100.
So it's what portion of the solution's weight is the solute, right? Like a percentage score, but for chemistry.
Exactly. And they give a simple example. Example 7.2, percent by mass. You have 10 grams of salt dissolved in 90 grams of water.
Okay.
The total mass of the solution is 100 grams. So the percent by mass of the salt will be 10 grams divided by 100 grams times 100, which equals 10%.
So a 10% salt solution, 10% of its mass is the salt, the other 90% is water.
Precisely. Now moving on to section 7.3 on page 3, percent by volume. Similar to percent by mass, but instead of mass, we're using volumes.
So how much of the solution's volume is the solute?
You got it. It's defined as the volume of the solute divided by the total volume of the solution, again, multiplied by 100. And they give us an example, example 7.3% by volume. We have 50 milliliters of ethanol mixed with 250 milliliters of water. Total volume would be 300 milliliters.
Okay.
So percent by volume of ethanol, you divide 50 milliliters by 300 milliliters, multiply by 100. That gives you approximately 16.7%.
So it's all about like what proportion of the solution is the solute, whether it's mass or volume.
Exactly. And these different ways are useful in different situations. Percent by volume is often used to describe the alcohol content in drink.
Oh, that's a good point. Like 12% alcohol by volume.
Right. It means 12% of the volume of that wine is ethanol.
Okay, it's all making sense now. What's next?
Okay. Section 7.4 on page 3, parts per million ppm. This one's used for very small concentrations where the solute is tiny compared to the solvent.
Like finding a needle in a haystack, but in liquid form.
Yeah, pretty much.
Yeah.
And measuring these tiny amounts, it needs a specific approach. Parts per million is defined as the number of parts of solute per 1 million parts of solution.
Okay, that sounds a little complicated.
Yeah. Let's look at example 7.4 on page 3, calculating TPM. We have 0.0043 grams of oxygen gas dissolved in 100 grams of water. They calculate this to be 43 parts per million of oxygen in the water.
Yeah.
Essentially, for every million grams of the solution, 43 grams would be oxygen.
Wow, that's a tiny amount.
Right, so parts per million is often used in environmental science. Things like pollutant levels,
Oh, right.
or even tiny amounts can matter.
Like lead in drinking water, even a tiny bit's a big deal.
Exactly. Before we move on, anything else on concentration?
I think I'm getting it. It's like different tools for different jobs.
Exactly. Now, let's go to page 4. Section 8, predicting solubility for ionic compounds. This section gets into how we can actually predict if something will dissolve in water or not.
Oh, that's cool. I've always wondered if there's a way to know if something will dissolve or just sink to the bottom.
Well, section 8.1, solubility rules for ionic compounds, gives us some guidelines.
Okay.
It's basically a set of rules based on the ions in the compound. For example, all compounds containing group 1 ions, like sodium or potassium, are soluble in water.
So if I see sodium or potassium, I can be pretty sure it'll dissolve.
Exactly. And then there's some ions that generally form insoluble compounds, like carbonates, phosphates, and sulfides.
Okay.
However, there's exceptions to these rules. The document mentions some. For example, even though carbonates are usually insoluble, if they're with group 1 ions, like sodium or potassium, they become soluble.
It's like a chemical matchmaking game.
Yeah, that's a good way to put it. And to show how these rules work, they have example 8.1, using solubility guidelines.
Okay, what's that one?
It focuses on calcium carbonate, CaSO3. Calcium is a group 2 ion.
Okay.
Carbonates are usually insoluble unless they're with group 1 ions. Since calcium isn't group 1, we can predict that calcium carbonate will be insoluble in water.
So by knowing these rules, we can avoid wasting time trying to dissolve something that won't.
Exactly. It's like a cheat sheet. Now, another thing discussed here is saturation. The solubility of a compound isn't unlimited. There's a point where no more solute can dissolve and the solution becomes saturated. Anything less is unsaturated, meaning more solute can still be dissolved.
So it's like filling a glass of water. You can keep adding water until it's full, but any more will spill.
That's a perfect analogy. They give an example. The maximum solubility of potassium nitrate, KNO3, in water at STP, which is standard temperature and pressure,
Okay.
is 15 grams per 100 grams of water.
So if I try to dissolve more than 15 grams of KNO3 in 100 grams of water at STP, it just won't dissolve.
Exactly. The solution will be saturated. It's holding the maximum amount it can at that temperature and pressure. Now let's turn to page 5. We encounter solubility curves.
Solubility curves. Those sound interesting. What are those?
So section 8.2 on page 5, a solubility curve is a graph that shows how the solubility of a soluble substance changes with temperature.
Okay. So it's a visual way to see how much can dissolve at different temperatures.
Exactly. Imagine a graph, temperature on the x-axis, and the amount of solute that can dissolve in, say, 100 grams of water on the y-axis. Each substance has its own curve, and the shape of that curve tells us how its solubility changes as temperature changes.
Okay, I'm picturing it. But how do we actually use these curves?
That's where section 8.3 on page 6 comes in, interpreting solubility curves. It explains that any point on a curve represents a saturated solution at that specific temperature. If a point falls below the curve, it means the solution is unsaturated, and if it's above the curve, it means there's more solute than can dissolve at that temperature. It's supersaturated.
So it's like a visual guide to saturation. Can we see an example?
Absolutely. Example 8.2 on page 6. Using a solubility curve. It uses potassium nitrate, KNO3. Again, it tells us at 50 degrees Celsius, the solubility of KNO3 is 84 grams per 100 grams of water.
Okay.
So if we find 50 degrees Celsius on the x-axis of the curve and follow it up to where it intersects with the KNO3 curve, the corresponding value on the y-axis would be 84 grams.
Okay.
That point on the curve represents a saturated solution of KNO3 at 50 degrees Celsius.
Got it.
And what if we had a solution with only 70 grams of KNO3 dissolved in 100 grams of water at 50 degrees Celsius?
Well, since 70 grams is less than 84 grams that can dissolve, it would be unsaturated, right?
Exactly. That point would fall below the KNO3 curve, meaning it's unsaturated. You could dissolve more KNO3 at that temperature.
Okay, so solubility curves are like cheat sheets for figuring out if a solution is saturated or not at different temperatures. I'm starting to see how useful these are. Are there any more examples?
No, that's the last one in this chapter. Looks like we've covered all the key concepts and examples from the